Hello everyone, welcome to the presentation. My name is Liu. I'm a doctoral student from the Chair of Computing and Engineering of Ruhr-Universität Bochum. Today I'm very glad to introduce our paper. The title of our paper is An Ontology Integrating as-built Information for Infrastructure Asset Management using BIM and Semantic Web. This research is based on the current status of digitization in infrastructure projects. Two aspects of information management are considered. First, we have looked at the documentation of concreting in this type of project. Since the development of BIM, more and more 3D object models are used in the design and construction, but a lot of information is still only available as paper-based documents during the construction work. This information cannot be interpreted by computers and is also difficult to be linked with the object model. However, this information can be important in the operation stage, for example, for the analysis of the structural health. Therefore, we should try to keep this information structured and digitized. The other aspect is considering the storage of as-built data in the operation stage. Currently, the National Authority for Infrastructure in Germany has established its asset management system using a relational database. It is commonly used to save essential structure data. The integration of object model is often not considered in existing systems. The delivered model, for example, as IFC file, will be saved in a separate data store without relation to the data of the asset management system. And as mentioned for the construction stage, part of the non-machine readable data is only archived as paper-based documents. In this paper, we propose a solution for the combination of BIM and semantic web to improve the information management in the two phases of infrastructure projects. In this approach, we focused on the construction stage. In future research, we work on the asset management in the operation stage using the acquired information from the construction. Our developed solution enables to improve digitization and linkage of data in the construction process. Furthermore, it provides a basis for the automated transfer and create a basis for applying the semantic data related to the object model in operation. Here we have three foundations for our proposed solution. First, using ontology, we are going to structure and digitize the non-machine readable documents as semantic information. With the information container for linked document delivery, which is certified as international standard and shorted as ICDD, we will collect the different data and documents as a whole data package. Within the container, the links between data can be built up. The entire data package provides a reusing data in future applications. For further cases, we are going to introduce a use case with general process for data collection with the information container. Here in the methodology, you can see the general process as mentioned before. There are 7 steps which can be divided into 3 major points. As preliminaries, we first define a use case. Therefore, we choose the most executed work in a bridge construction project, the concrete placement. Regarding this use case, we analyze the workflow and determine it in a process map. We focus on the data exchange during the process and identify information requirements. After the preparation, we consider which ontology we need to capture the data. In this case, we need to define an ontology for the concrete placement and integrate it into the container template. In the evaluation, we establish the container template on the ICDD platform and use it to collect the information. For the simulation of the handover, we can use a Spark query to select the particular data. In this slide, we present the process map for the concrete work. In the use case, It includes the documentation of activities of concrete placement as shown here, and the quality assurance of the material properties as shown here. Here in the process map, you can see 3 lines for the participants which we have considered. Here the contractor mostly executes or induces the activities in the whole process. The laboratory performs the most of tests for the material properties, and the client or site observer is involved in checking and acceptance of the work. To regard our purpose of collecting the as-built information, we focus on the data generated during the whole work process. It is an interactive process between the contractor and the laboratory with many data exchanges. Combined with the national technique standard, as we used here the German guideline, for example, DIN IN 1045, we can identify the information requirements. It supplies the basis for modeling the ontology. Then we develop the building concrete monitoring ontology. It is a domain-specific ontology using web ontology language. As you can see in the diagram, there are 8 classes defined in the BCOM. 3 green-colored classes are for the concrete activities, and the red-colored classes for the quality assurance of the concrete properties. The object properties build the relations between the classes, and the data properties refer to the alphanumeric information, such as the begin time of the concrete placement. The details of the properties can be found in the documentation of the ontology. For more test procedures, the class test can be inherited. And for the description of the organization, such as laboratory or people, we have used the existing ontology V card. Once the ontology is defined, we can use it for the collection of semantic information from paper-based documents. We consider the major documents of the concrete work in the ontology, and these are created as instances of the related classes. This ontology can still be extended with more test procedures as mentioned before. We are aware of the unit definition for the literal instance and planning to address this issue with integrating the QUDT in the next version of the ontology. The ontology is declared in the permanent namespace with the prefix BCOM. For the quality, we have checked it with the ontology pitfall scanner, and you can also find the source in our GitHub repository. Now we are able to create the information container to capture the as-built data. The container has a general structure that is defined by the respective standard. It contains 3 folders. One is for the ontologies we use, one is for all the payload documents, and the third one is for the linked data sites. The content of the container is also defined in the table here on the right-hand side. The respective ontologies and the object model must be integrated into the container template for the use case. During the work process, we can upload documents, capture data, and create links between the instances of the ontology and the IFC objects in the container. To realize the container, we use the ICDD platform. It is created in a preview research, and the development is still going on. It establishes a web-based environment and provides access to the information for different participants. To provide the provided functionalities like creating the container, adding data, uploading different documents, and setting up the links, simplify the data collection and exchange as a one data package. With a Spark query, we can select the particular information as needed. The query can also be executed through the query panel by the ICDD platform. On the right-hand side, we show a video about the platform. Here you can see that the related information container can be managed in one project. In the container, the object model can be presented with embedded IFC viewer. In the total file, concreting documentation, the information of concrete placement are collected as instances of BCOM. Here is the query panel. With this query, we can select all elements of the IFC model with the constraint that the concrete was delivered by a specific concrete supplier. More queries could be employed in the same way, such as query for the fresh concrete properties of a certain IFC element, or get the contact information of the laboratory that performs the respective test of the hardened concrete. So as you have seen in the evaluation, with the BCOM ontology, we can improve the digitization of the documentation of concrete work in the construction. The ICDD platform with the available functionalities provides a basis to integrate information in view of a life cycle-oriented asset information modeling. In the quick recap, we show the simple workflow to use BIM and semantic web in form of ontology and information container for an individual use case. In the future, we will define alignments between the BCOM and other existing ontologies for the construction domain, such as building topology ontology for more compatibility. And for lifecycle information modeling, further implementations with more functionalities of the platform, such as integrating existing asset management system, are planned. Here you can find further information and sources on the BCOM ontology using these QR codes or hyperlinks. So thank you for attending the presentation, and please feel free to ask your questions.